In this video, we are going to be moving on to the next part of the electromagnetism video series that I'm currently doing and going on to look at magnetism. Now, magnetism as a topic can sometimes cause a little bit of headaches because some of the concepts that come from electricity, like the previous stuff that we've covered in this module, can be applied to magnetism, but it doesn't apply in quite the same way. And I think that can lead to a hell of a lot of confusion between the two, because in some ways they're very analogous, and we talk about magnetic fields very similar to how we talk about electric fields. But everything is just a little bit different. And in this video, I hope to elucidate why things are just a little bit different when we come to talk about magnetism. For this next video, we're going to be mostly covering a lot of stuff that hopefully should be familiar to you, but just again, kind of formalizing it using more mathematical notation. So we're going to be having a look at charged particles moving and how that both creates a magnetic field and they can be responded to an external magnetic field. And we're also going to be having a look at how currents flowing in wire are going to produce a magnetic field. So let's get on with the video. So the very first thing I want to say about magnetic fields before anything is that magnetic fields are, at a fundamental level, an extension of electric fields. So of course we said an electric field is produced by a charged particle. So we have a positively charged particle right here, and we said that it produces a field, an electric field that kind of goes radially outward from the charge right here. So it produces an electric field that is spherically symmetric, with the origin point being this charge. Now, at its core, the only thing that really causes a magnetic field is if this charged particle moves in space. So let's go ahead and get our charged particle and just move it through space. Whilst it is moving, it is producing a magnetic field. But when it stops moving, like here, it will no longer produce a magnetic field. That is the only thing that causes a magnetic field. Now, some of you might be aware of the idea of spin, which is an intrinsic magnetic field. And for now, we're not going to be really considering spin. This course kind of starts at more classical terms, and spin is a quantum effect. But you'd be right to think that spin is one of these things that does produce a magnetic field, and that is not intrinsically produced by a movement of charge. Although most people tend to think of it as a rotation of charge, which again counts as movement, and therefore you can kind of think of it, because it's spinning, as a magnetic field generator. But for now, all we need to know is that magnetic fields are caused by a charge that is moving in space. Now, what was found experimentally in regards to how big this magnetic field that is produced by, say, a charge moving through space is that it was empirically found that the magnetic field, which we often give the term B, this is often called the magnetic field strength, or sometimes you might hear it referred to as the magnetic induction, but I will just be referring to it as the magnetic field strength. This is proportional to the velocity of the particles. So if it was to move quicker, this would produce a larger magnetic field than if it was to move slower, right here. So it was found that experimentally that the magnetic field was directly proportional to the velocity. And additionally, you find that it's also directly proportional to the magnitude of the charge. So if you increase how much charge this object has, then you find that the magnetic field increases. So even if you have a charge moving at the same velocity, you actually find that the charge which is bigger in magnitude will have a bigger magnetic field. And the final thing that was found is if you measure the magnetic field as a function of distance, of course it's going to, similar to an electric field, matter how far away you measure it, you actually find that you get a very similar thing to what you find with electric fields. In fact, you get this 1/r² relationship. So you double the distance away from where you're measuring this magnetic field, then you essentially find that the magnetic field decreases by a factor of 4 in accordance with this 1/r² relationship right here. So this is what was kind of empirically found about the magnetic field B right here. However, of course, this is a moving particle, so how we measure it is going to be sort of a little bit tricky to visualize and a little bit tricky to get your head around. So if you are a static observer measuring the magnetic field of this charged particle moving through space, well, this charged particle is technically moving away. And so although it has a velocity, the distance is constantly decreasing. And the angle between where this charged particle is moving, so this kind of velocity vector, and the position vector between the observer and the charged particle is also constantly changing. So it's important to bear in mind that this v is the relative velocity between the observer and the charged particle. So as well as all this, we actually find that the magnetic field, as I said just before, is also directly proportional to the sine of the angle right here. So if we have this position right here, you find that the angle is nearly 90 degrees, so you're going to get a maximum magnetic field. But if we change where we are, keeping the same distance more or less, we actually find that the magnetic field goes down significantly to 0. And so there would be no magnetic field if you observe the magnetic field along the trajectory of this charged particle. Whereas if you go back to where you were before, then you find that you get a much higher magnetic field. So it's maximum basically at right angles, which is what sine theta is telling us. Sine theta is a maximum at 90 degrees because the sine of 90 degrees is 1, which is the maximum value. So if we put all this together, we find that the magnetic field is proportional to the charge times the velocity times sine theta, all divided by r squared. And whenever we have a proportionality relationship, we can define a constant term. We can define it being equal to a constant, which we normally just call k for now, multiplied by qv sine theta divided by r squared. Now this constant term actually has a very solid value. This constant is actually 10 to the power of minus 7. And the way in which this is defined is if you have two wires with current flowing, they'll produce a magnetic field if they're 1 meter apart of a certain value. And that's actually how this constant is defined. But what is actually more common is instead of defining this as a constant, is that you actually define a quantity known as the permeability of free space, mu naught, which is equal to 4 pi times this constant right here. Very similar to the 1 over 4 pi epsilon 0. So in fact, instead of writing this in terms of k, we actually write this in terms of mu naught, which is called the permeability of free space. And it's defined using this current in a wire analogy, but we're going to go on to what that is in a little bit more detail in a later portion of the video. So we say that B is equal to mu naught over 4 pi times QV sine theta divided by r squared. So this is kind of our empirical equation for how strong the magnetic field strength is if you're an observer watching an electric charged particle moving at velocity v right here. But when we get to this level, B is no longer really a scalar quantity because a magnetic field or any kind of vector field has both a magnitude and a direction. It is a vector quantity because of course it is telling a certain particle to move in a certain direction. So obviously this field right here is going to have a value everywhere in space, and it's also going to have a certain direction, which could also depend on where you are in space. And this is exactly like the electric field, where we had a charged particle and we had electric field lines, which we could represent as arrows coming out of the charged particle, which of course would be less strong the further away you were from the charged particles. So the smaller arrows here are representing the fact that the electric field strength is less at large distances. So with any vector field, we really have to be describing this in terms of vectors. And so how are we going to vectorize this equation right here? Well, we notice that b is proportional to the sine of theta. And whenever we have something proportional to sine theta, we can actually refer to the cross product of two vectors. So what do I mean by that? Well, whenever we calculate the cross product of two vectors, so let's say we want to calculate the cross product A cross B, and let's say that this is going to be equal to some vector C right here. So C is equal to A cross B. Well, what we can say is that the magnitude of C is equal to the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between these two vectors. So just for example, if you have two vectors that are at 90 degrees from each other, then you get the maximum cross product, which points perpendicularly to both right here. However, you take the other extreme, and if you have two vectors that are not oriented along the axis, let's say they're both oriented along the x-axis right here, well, there's going to be no angle between these two vectors, and therefore you get that sine of theta being 0 is also equal to 0, so you actually find that there's no vector even formed. So whenever you have a kind of sine theta relationship right there, that kind of screams cross product. And it would be the opposite if it was a cos theta relationship, because that would be the dot product between two different vectors. So what in fact are our vectors? Well, we know that velocity is technically a vector right here. So velocity is one of our vectors we are considering, and this is the velocity of our charged particle. But of course, the other vector we are considering is the distance between the observer and our charged particle, which is moving at a certain velocity. And this is exactly what I said before. We found that empirically, when we were at 90 degrees, when this charged particle was here, so tangential to the position vector, which is of course here to here, and this is our velocity vector, this angle right here is 90 degrees. So we found that the maximum magnetic field is maximum at 90 degrees right here. So sine of 90 is 1, and therefore you just get the maximum possible value right here. So we also now know that b as a vector is proportional to the velocity v of our charged particle cross-producted with the position vector r right here. So this is kind of the vector way of saying what we said before. And this of course takes out this kind of sine theta dependence because that's already encoded within the cross product. But we don't really have an r vector term in this equation right here. But of course we have an r squared term, and we can just use the identity with any vector in that a vector is simply equal to the magnitude of that vector times the unit vector. So essentially this term encodes the magnitude of how big the vector is, and this term is always going to have a magnitude of 1, but it just encodes which direction it's pointing. The purpose of a unit vector is just to point in a certain direction. So what we can actually write is, instead of writing this as a scalar equation, because of course we're trying to turn it into a vector equation, so whereas we had this 1 over r squared in the scalar equation, if we're going to turn this into a vector, we can simply say that b is simply proportional to 1 divided by r squared, but of course we have to add a vector, and we just say that that's in the r hat direction right here. But what did I say before? We could use this identity in order to transform this equation, as rather than being 1 over r squared r hat, we know that r hat is equal to r vector divided by the modulus of r cubed. I've taken out these kind of modulus signs right here because of course this is the modulus. So we can also say that this is equal to r vector divided by r cubed. And this is the more typical way of expressing how the b vector is dependent on r. It's not actually a 1 over r cubed relationship like this would imply, but this is just a much more easy way of expressing this mathematically, and you actually find that the algebra is a lot more simple if you express it in this way. So taking our equation, you can actually write that b vector is equal to mu naught over 4 pi times q multiplied by our velocity vector right here, so now we're on to the vector part, cross-producted with our position vector, r right here, divided by r cubed. And you can also express this as, so that's an equivalent way of expressing it using what we just did up here, but more commonly it will be written like this. So I just wanted to do this little roundabout exercise just to show that that is the more common way of expressing it. So this equation gives us what the value of the magnetic field is, but it doesn't give us what the value of the force that results from that magnetic field is. Now, if we want to work that out, we actually have to turn our attention to the relationship between charged particles moving, magnetic fields, and forces. And hopefully you'll recall that these three quantities are all at right angles to each other. So if you have a charged particle moving at a velocity v, and you have a magnetic field that is oriented perpendicularly, then you find that the force is perpendicular to both the magnetic field and the direction of velocity of the charged particle. So from before, we know that the magnetic force, which I'll just write as a scalar for now before turning it into a vector, is equal to the product of the magnetic field strength B times the charge times the velocity. And this is the case if B is perpendicular to V. But more generally, we say that it's BQV multiplied by the sine of theta if the magnetic field and the velocity are not at right angles to one another. So this is an equation that hopefully everyone is familiar with. So what is the magnetic force as a vector equation? Well, again, we have a sine theta right here, so we can in fact write this force as being equal to the cross product between the b vector and the velocity vector right here. And of course, the only quantity that's not a vector is charge. That's just a simple scalar. So we can add that outside the front, and we can say that the magnetic force is equal to the charge multiplied by the B field cross-producted with the velocity field right here. And that already encodes our sine theta, and it keeps our equations in vector form, which is what we want because force is a vector, velocity is a vector, and field is a vector. So that is our magnetic force on a particle caused by an external magnetic field right here. But what if we also happen to have an external electric field as well for some reason? This is a fairly likely scenario. Well, we know that the external electric field is simply equal to the charge times the electric field right here. And this is a simple proportionality relationship right here. And so this tells us that the electric force runs in the same direction as the electric field lines. But of course, this is slightly different right here. We actually find that the magnetic force actually runs parallel to both the magnetic field and the velocity of our charged particle right here. So this actually illustrates a real difference between both electric and magnetic fields right here. So whereas if you have a charged particle, say, moving through an electric field, so say we have our charged particle moving here, it has a velocity here, and our electric field runs parallel, well, our positively charged electric field is going to be attracted to the negative end, so it's just going to move in the same direction as the field lines. But this isn't the case with a magnetic field. If we now replace our electric field with a magnetic field, then what are we going to get? Well, our charged particle is moving to the right. Our magnetic field is going to be moving upwards. What's the force going to be? Well, the force is going to be both perpendicular to this direction and this direction right here. And what is going to be perpendicular to both? Well, this is going to be in a third dimension, which we often represent using either this symbol here or this symbol right here. This basically means going out of the plane of the diagram, and this basically means going into the plane of the diagram. And of course, you can kind of think of this a bit like an arrowhead. So if the arrow is coming out of the diagram, you will see the point of the arrow, the very tip of the arrow. Whereas if the arrow is going into the diagram, like here, you'll see the feathers on the arrow, which is like that. So that's just an easy way of telling the difference between both of these symbols right here. And so if we apply this rule right here, B cross V, well, if V is going along this direction and B is going up along this direction, you actually find that the force is coming out of the diagram rather than in the diagram. So this means that this charged particle will experience a force that is coming out of the diagram. But this particle is kind of already moving in a direction that is at right angles to the force. So what's actually going to happen in this case? Well, this means that the charged particle will actually curve in a circular direction, sort of out of the plane of the diagram. So it's a little bit hard to draw right here. I did choose a maybe not the best example, but this charged particle will actually come out of the plane of this diagram right here and bend in a circular arc right here. So that is what's going to happen when we apply a magnetic field, and that is a big contrast to the electric field, which is of course in just the same direction. So what happens if this particle stops moving entirely? Well, if this particle stops moving entirely, and we have this magnetic field right here, well, V is 0 from this equation. So if V is 0, then F magnetic is 0, so there's going to be no force on this particle, and it's not going to move, essentially. It's going to be completely stationary within the magnetic field. So the only thing that a magnetic field will influence are charged particles that were already moving before the magnetic field was applied, and then it will cause them to go in that circular arc. But if the charged particle is not moving, then applying a magnetic field will do absolutely nothing. And this raises an interesting question about the magnetic field, because of course an electric field right here will accelerate a charged particle. But a magnetic field will not change the magnitude of the velocity of the charged particle, it will only change its direction. And because of course kinetic energy is proportional to v squared, it's 1/2 mv squared, if the charged particle does not change its magnitude of velocity, then it's not doing any work, is it? The kinetic energy is simply staying the same, as opposed to the electric field case in which the acceleration is non-zero and therefore work is being done. So magnetic fields, unlike electric fields, do not do any work on the charged particle. And there's actually a nice mathematical way to prove that, is that if you take the power of any system is given by the product of force times velocity. But as a vector, you actually take the dot product between the force vector and the velocity vector. So what happens if we try and take the dot product between the force and the velocity? Well, in the case of our magnetic force, we get that this is equal to Q, V cross B, dot producted with V, right here. But what is this going to equal? Well, V cross B, the cross product between the velocity and the magnetic field, is going to return a vector that is perpendicular to both the velocity and the field right here. But what happens when we said if we take a dot product between a vector, two vectors that are perpendicular? You get 0 right here. The dot product between, say, this vector A and this vector B right here, if they're at 90 degrees, this dot product is going to equal 0 right here, because of course dot product is proportional to cos theta, the angle between the two vectors, and cosine of 90 degrees is 0. So that means that the power done by any magnetic field is simply equal to 0. So this tells us that no work is being done because the power, the rate of change of energy, is 0. So magnetic fields do not do any work. And that is a very important point to note about magnetic fields, and is in stark contrast to electric fields. Now I want to consider what happens when, instead of having a single charged particle, which is what we've been considering so far, we actually have a current. And what do I mean by a current? Well, typically in electricity, we have a current which is full of a stream of electrons. So this could be a stream of electrons in a wire, for example. You could actually have currents that form for other reasons, but essentially a current is just a steady stream of electrons right here. Now, we already said that one charged particle produced a magnetic field, But when we have a steady stream of charged particles, we actually get a current flowing. And because, of course, these are all charged particles, we're also going to get a magnetic field right here. So we said that the magnetic force right here as a vector is equal to Q times V cross B right here. But what is Q right here? What is the charge? Well, the charge is simply equal to the current multiplied by the time, delta t, so within a certain time window, for example. And of course, this, to be mathematically correct, this would be the change in charge, the number of charged particles that are passing a singular point. So, and that is what the current is right here. So we can substitute in this equation, instead of Q V cross B, instead of Q right here, we can put I delta T. So we can say that the force is equal to the current times a time interval, multiplied by the cross product between V and B right here. But of course, delta T times V is just simply going to be a length term, because speed equals distance over time, therefore speed times a change in time will just equal a length. And so what are we going to call this length? Well, this is going to be the amount of distance that an individual electron will have covered in time delta t. So we can just call this L for now. So that is L, and that is equal to V delta t. And we're just simply going to go ahead and call this L a vector right here, just in order to keep the velocity vector right there. So we're going to say that this is IL cross B right here. So this is the force. Now here we get to a real kick in the pants that physicists have ended up in, just simply because of the way in which conventional current is defined, which is opposite to the actual flow of electrons. So we actually simply have to reverse this, because of course conventional current actually flows in the opposite direction to which electrons flow. So we actually multiply this whole thing by -1, so we actually get that the force is equal to minus IL cross B. And because the cross product is anti-commutative, that is to say that A cross B is equal to minus B cross A, we can just simply say that this is equal to I B cross L right here. And if we're just going to convert this equation into a scalar, then we can just simply say that the force is equal to BIL if everything's at right angles and everything lines up neatly. It's not perpendicular, it's going to be multiplied by the sine of theta, as we said before. So we're going to get that the force is equal to BIL sine theta, where theta is the angle between the magnetic field and our B field right here and the current flow right there. So hopefully that equation is familiar. This is just a way of talking about the force acting on a wire which is carrying a current which is suspended in a magnetic field. Now, a lot of the time in electromagnetism, we don't actually talk about current, like this I term right here, because of course we've seen that current is technically a scalar, but we kind of want to try and describe it as a vector quantity. And we typically use the quantity called J, which is known as the current density. And I think I've probably mentioned this in previous videos, but I'm just going to redefine it here just so everyone's aware. The current density J is equal to the current flowing divided by the cross-sectional area in which the current flows. So if we have a wire right here, cylindrical wire, and we have our current flowing down here, then obviously it's going through this cross-sectional area. And so if we divide the current by the area, then we get the current density J. And J is a vector quantity. J is the vector quantity that points in the same direction as the current flow, which is obviously opposite to the actual direction in which the electrons flow, just because current is defined oppositely. So more formally, we say that J is equal to the rate of change of current with area. We typically take it to be in the z hat direction, but it isn't necessarily in that direction. It's just in the direction it's propagating, which I will just say is the z hat direction. Or you could express this as an integral by saying that the current is simply equal to the integral over the surface of the current density J right there. And it's going to be a dot product with the surface. Now, whenever we're talking about charge flowing, we always make the rule that the amount of charge flowing into an area has to equal the amount of charge flowing out of an area. That's kind of like a fundamental thing in physics. You can't have charge going somewhere and then have it magically disappear. It has to go out if there is charge going in right there. So how do we quantify this? Well, since we said that the current is equal to minus the rate of change of charge, if we're dealing with a typical wire, then we can substitute into this equation and get that minus the rate of change of charge is equal to the integral of the current over the surface right there. But in previous videos, we've talked about this idea of charge density, where we have this charge density rho being equal to the charge per unit volume right there. And this generally applies for a non-uniform charge distribution. Of course, it would simply be equal to Q divided by V if it was uniform, but if it's in a more general case, then we have dQ by dV is equal to the charge density, charge per unit volume, rho right there. So instead of writing it in terms of the total charge, we can write this in terms of the charge density. So that's going to be minus d by dt. And if this is the differential form, we can just say that this is equal to the integral of the charge density over the volume right there. And that is equal to J dot ds right there. But of course, we can apply the divergence theorem, as we have used many times throughout the series, in that if we have something integrated over a surface, we can actually express this as a volume integral. And so we can say that this is also equal to the integral over the volume of the divergence of whatever this vector is, which in this case is J, integrated over the volume right there. So this is what we end up with. But of course, we're integrating over the exact same volume right here. So we can actually remove these integrals and say that minus d rho by dt is simply equal to the divergence of J. And this is what's known as the continuity equation for current flow. And it's basically saying that you have to have as much charge flowing into an infinitesimal volume as you have coming out. So the flux has to equal the amount of charge that's flowing in minus the amount of charge flowing out right there. Now, if this term on the left is equal to 0, which basically equates to there being a steady current, a steady unchanging current, then from this equation we can actually say that the divergence of this J vector is also equal to 0 right there. And this is kind of like the condition which we say mathematically for there being a steady current. But how does this affect the magnetic field right here? Well, we said earlier that the magnetic field in terms of the current is given by mu naught over 4 pi times Q, the charge right here, times V cross R hat divided by R squared right here. But we can express, as we said before, QV, this product right here, as being equal to the current times the length right there. That's what we kind of did by just kind of dividing one side by charge and then multiplying the other term by charge. So we're going to get, instead of this, we're going to get mu naught over 4 pi, and we're going to get current times our length vector right here, crossed R hat, divided by R squared right there. Now, if we take a really, really short section of wire that's carrying a constant current, and we're going to call this dl right here, an infinitesimally small change in our length, then we're going to result in an infinitesimal magnetic field, dB right here, which is essentially just going to be the same. You're going to get all this stuff out the front, except we're now just going to get dl cross R hat divided by R squared right here. But we can go further. We can say that instead of writing this in terms of the current, we can actually write this in terms of the current density, and we can do this by dividing this term by area to get the current density, but also multiplying this term by area. And what's going to happen when we get dl times an area that's perpendicular, then we're going to get a volume term right there. So we can also express this relationship as mu naught over 4 pi. And of course, volume is a scalar, but now current is a vector. So let's just go ahead and change where we're going to put our vectors right there. We're going to get J right there cross r hat divided by r squared times dv right there. And now if we integrate this, if we express this as an integral of the total magnetic field, not just an infinitesimally small part of it, we're going to get mu naught over 4 pi times the integral of j cross r hat divided by r squared over the volume. So that's going to be a volume integral right now, where typically you'll be integrating over a cylinder, although not necessarily. And the current's running in this direction, and you have your area that's cross-sectional right there. And whereas before we were considering a length, now we're considering the whole volume of this cylinder right there, and you're integrating over the whole entire thing. And like we said before, we can also express this as mu naught over 4 pi over the volume integral, and instead of r hat divided by r squared, we can express this as r vector divided by r cubed over the volume right here. Now I'm just going to step aside for a second and evaluate a certain derivative. And I'm going to consider what the gradient, which is of course our vector operator, of 1 divided by r is right here. Remember, gradient is a vector operator that acts on a scalar to produce a vector. Well, the gradient of 1 over r, this is just going to be the derivative of 1 over r with respect to r. And that's just going to give us 1 over r squared, but with minus sign out the front. But we said earlier that 1 divided by r squared can simply equal minus r vector divided by r cubed right there. So we can actually substitute this in right here because we have a cross r vector divided by r cubed. So we can go ahead and substitute in for that right there. And of course, since we said the cross product was anti-commutative, we can just go ahead and reverse this integral sign right there, just to get rid of the minus sign. Now, if we think about where we're evaluating our integral over, this is a volume integral that exists within the actual wire. But when we have a look at this derivative term right here, this is actually the derivative that's outside of the wire right there. This whole gradient of 1 over r, this r is the evaluation point that's away from the wire. This r is how far away we are. So essentially we have a derivative and an integral that are acting over two different coordinate systems. So we can actually use this to manipulate this integral right here. We can actually go ahead and bring this del term right here outside the integral because it's not acting over the integral coordinates. And we can in fact just put our integral over j divided by r dv. And then we can actually put this cross operator outside the integral. We can just sort of do the integral first over j, and then just put this cross operator outside of the integral because, of course, this acts on a different set of coordinates to this right here. So that's a little bit of a tricky step, but basically, essentially, we have two different coordinate systems, and so this acts on a different set of coordinates than this volume integral, the coordinates in which the integral is being evaluated over. Now, I want to ask the question, what happens when we take the divergence of the curl of any vector? Well, the mathematicians have come to our rescue for this, and they have derived this formula, this very nice result, that if you take the divergence of the curl of any vector f, you will always get 0. And this will hold true for any single vector right there. So what happens when we take the divergence of RB? Because remember, this is all the magnetic field right there. Well, the divergence of B is simply going to be equal to, well, the divergence of whatever's on this side. So all this right here. So we're going to get mu naught divided by 4 pi times the divergence of the curl of all this stuff right here. But of course, we said that the divergence of the curl is equal to 0 for literally any single vector. This is still a vector right here. So what's going on here? That means that this whole term is going to equal 0 on the right. So because that's true of any single vector. So we get the result that the divergence of B is equal to 0. And this is what's known as Maxwell's second law. And it's basically a way of saying that you cannot have a magnetic monopole. So if we take a magnet right here, let's take a typical bar magnet, you'll have a north pole and a south pole right here. But you cannot just have the north pole on its own. And of course, this is in stark contrast to the electric field, where of course you can have a positive charge right here, completely separate from a negative charge. It doesn't have to be a dipole or anything like that. Whereas with a magnetic field, you actually cannot get a north pole like that, a singular north pole. It just doesn't work like that. And the reason why this kind of means that you can't have a magnetic monopole happens when you integrate our magnetic field over a surface right here. And this right here is what's known as the magnetic flux, which I'm just going to give the symbol phi, subscript m. And this will apply for any closed surface right there. But what did we say? We said we could use the divergence theorem to express any surface integral in terms of a volume integral. So we can actually express this as a volume integral of the divergence of B over the volume right there. So that is the magnetic flux. But we just derived that the divergence of B is 0. So that means that phi m is just going to equal 0 because this term has to equal 0. And so we get the result that you cannot have a net magnetic flux. This must mean that the magnetic flux that goes in must equal the magnetic flux that goes out. So the net flux is equal to 0. And so if we take the case where we have a magnetic monopole right here, so if we have our north pole, but we're just going to go ahead and pretend that this exists right here. This is going to emit a magnetic flux that's going to sort of emit outwards or something like that. I mean, for this example, we know it's not moving, but let's just pretend it's moving for a sec. Well, that's going to give a non-zero net flux coming out of this surface right here. And that's going to violate this law right here, Maxwell's second law. And so that is why you cannot have a north pole on its own. You cannot have a magnetic monopole. And this is very different again to the electric case, where this electric field is perfectly allowed to produce a net flux of electric field passing through this surface right here. Of course it can, but you cannot have this situation right here with the magnetic field being a monopole. And so this is a big difference between electric fields and magnetic fields, is that you cannot have any magnetic monopoles. You cannot have a north pole without a south pole. It has to be dipolar. You have to have one with the other. And that is not the case with a electric field right there. So that's going to be it for today's video. In the next video, we're going to have a look at Ampere's law, which is actually another one of Maxwell's equations. And we're going to go ahead and consider how you can derive the magnetic field directly from the current that's flowing within the wire right there. So I hope that was useful, and I'll see you guys in the next video. Bye-bye.